Then, if you have C1 and C2 inside the surface S, they are curves. And for example, if this S is the projective plane, then I can consider the intersection number can be extended to a bilinear form on the set of divisors over the projective plane. Here you just, for each of these two curves, you take the bilinear form. The bilinear form here can be given by C1 and C2. Then the value on this pair is given by the intersection number of these two curves. So you just extend this formula linearly to the set of divisors on the projective plane. Then we know that actually C1, C2 should be equals to the degree of C1 times the degree of C2, and then you just use Z linearity to extend it to the set of divisors. And in particular, you can. So here, if this is true, you need to assume that the two curves are different. But if they are different, you still want the same equality holds, then you can just define this value to be the square of the degree of C. So this is the case for the projective plane. We can define such a bilinear form on the set of divisors. But this definition, the fact is that this definition can be generalized to arbitrary S. Well, in other words, if you have a general surface S, you have the notion of divisors, and then we can still have a bilinear form on the set of divisors over the surface S. The value is in the interval. It is bilinear, and when you have two different curves, you still have the geometric meaning. Namely, if you have two curves, then the value of this bilinear form on this pair is given by the number of the intersection points of the two curves. But the self-intersection number is a very tricky one. Because on arbitrary surface, you cannot, this may not be true. The intersection number may not be the product of the degree if the surface S is not a projective plane. But in general, we have another special property. We have, if you consider a curve and the rational function on the space on the surface S, again, similarly, you can associate a divisor associated to this rational function. You just consider the zeros of the rational function, consider the poles. But here, the zero and poles are one-dimensional, so they are curves on the surface S. So this gives you a divisor on the surface S. You consider the value of on curve C and such a principal divisor. You can show that this is always zero. So in other words, if one of these entry is a principal divisor, then you always get zero. Then by this, we can define the self-intersection. The self-intersection, actually this is not a very strict definition, but we can. So if you have you have the same curves, you intersect the same curve, you get the whole curve, and it is impossible to count points on a curve. But you can change this curve C by some other curve C prime. So here this C prime is another curve. And linearly equivalent to the curve C. If you can find such a curve, as a divisor, it is linearly equivalent to the curve C, then the difference of C and C prime is a principal divisor. So if you have this property, then it tells you that these two, the value of these two bilinear forms should be the same. But the problem is sometimes you may not have such a curve. You may not find a curve on the surface S, which is linearly equivalent to the curve C. But in general, there is a way to define the self-intersection number. And the most important thing about the self-intersection number is that it is different from the in the case of projective plane. Here, the self-intersection number is always positive in P2. But in general, if you consider an arbitrary surface, this intersection number might be negative. So I will give you some example of a self-intersection number, which is negative. But before that, I want to explain why we care about the intersection number. The reason is you can express the intersection number, or you can express the number of rational points on a curve or finite field as the intersection number. So now we are back to the proof for the Riemann hypothesis for curves over finite field. Here, assume we have such a projected smooth curve, and I consider from this curve, you can consider a surface. Just make two copies of the curve C, then you get a surface. And inside this surface, I want to consider some curves. So the first one, this gamma, is the image of the map C goes to C times C. We consider embedding from the curve C to the surface S, such that in the first component, it's just an identity component, and the second component is the Frobenius. Okay? And then this gamma is the image of this map. So in other words, if you write it in terms of points, it maps X to X and Frobenius X. You know, the Frobenius map is just raise the coordinates to the Q's power. Secondly, I consider another curve inside the surface S. I denote it by delta. Delta is just a diagonal. So what is a diagonal? It's just, again, you consider a map from C to C cross C. Then both of the map are the identity map. Okay, so the image looks like you map X to XX. This is a diagonal. And finally, I still have two more curves. I just fix the points. Inside on the curve C, it may not be defined over FQ. It's just a closed point defined on the curve C. Then I define F1 to be C times the point P, and F2 is P times C. So these two curves are on the surface S. But they are not defined over FQ, they are defined over FQ1. Under this definition, I have the following lemma. If you compute the intersection number of gamma, this curve, and the diagonal curve, then you just get NQ. NQ is just the number of FQ rational points on the curve C. And if you consider the self-intersection number of the diagonal, you get 2 minus 2G. And if you consider the self-intersection number of the curve gamma, you get Q times 2 minus 2G. Finally, if you consider the intersection number of gamma with these two curves. The first one is Q, second one gamma with the intersection number with F2 is given by 1. So these are some computation of the intersection numbers. For example, the first one, I want to consider the intersection number of these two curves. So that means any curve on gamma is given by x for Venus x, and any curve on the diagonal is given by y1. So if you want this point to be an intersection, x should be equal to y, and x should be equal to Frobenius x. So this intersection point has a bijection with the set of FQ rational points, or has a bijection with the set of points which is invariant under the Frobenius. But that's are exactly the points which are defined over this line. So this is why you have the first results, and this is not very easy to, not very difficult to check. This is not very difficult to check, but these two are not very trivial if we use the so-called adjunction formula. I do not have time to explain here, but you can take a look at the notes to see the proof. So we are pretty close to the proof of the Riemann hypothesis. We still need one more theorem. So then D be a divisor on the surface C times C. This is the surface I've just defined. And F I denoted by D1 to be the intersection number of this D with the curve F1, and then I denoted by D2 to be the intersection number of the divisor D with F2. Then I have the inequality. The self-intersection number is always smaller or equal to 2 times D1 times D2. So this is a very difficult inequality to prove. So we have to assume this fact in order to prove the Riemann hypothesis. So if we assume that theorem, in the theorem, I take D to be R times gamma plus S times delta. Gamma is the image of the graph of the Frobenius, and delta is the diagonal curve. For any pair of integers R and S, I have such a divisor. And if you compute the intersection number of this divisor with F1, you can just use this lemma together with the property that the intersection number is bilinear for both of the components. This intersection number is given by RQ plus S, and the intersection number of the divisor with F2 is given by R plus S. Then that theorem tells you that the self-intersection number of the divisor D should be less or equal to 2 times RQ plus S times R plus S. But this one, because this is a linear combination of gamma and delta, these intersection numbers have all have been listed here. So you can use the bilinearity of the intersection number to compute the left-hand side in terms of the first 3 numbers and this here. So if you summarize it, you simplify it, it tells you that you have such, this inequality becomes G times Q R squared plus Q plus 1 minus N times RS plus G S squared is bigger or equal to 0. So you can regard this as a quadratic form for the variable R and S. And because these R and S can be taken arbitrarily, it means that as a quadratic form, it is always non-negative on any pair of integers. But you know the rational number is dense in the set of real numbers. That means this quadratic form is always non-negative. So that means the determinant should be always non-negative. So that tells you that just compute the determinants. The determinant should be negative. So that means the absolute value of this term should be less or equal to 2 times G squared Q. The square roots of these two coefficients. So in other words, as a corollary of the Riemann hypothesis, we know that this difference can be written as the sum of these 2G numbers, and this is less or equal to 2G times square root Q. So our aim is to prove that each of these alpha I has absolute value smaller or equal to square root Q. But here we show that the sum of their absolute value, the absolute value of their sum is smaller or equal to this number. This is, of course, does not imply that each of these number has absolute value smaller or equal to square root Q. But you can just replace here, we just regard C as a curve defined over FQ, and we do the computation. You just replace FQ by any finite extension of FQ. You do the same computation, then this inequality becomes alpha 1 to the m, because here then this is NQ, you should replace NQ by NQ to the m, and replace Q to the m by replace Q by Q to the m. So then the difference is just the nth power of these numbers. This is, should be less or equal to 2G times square root Q to the m. For any m, this is true. Then the Riemann hypothesis follows from the following lemma, which can be done by a clever high school student. That means state the lemma and finish it. So suppose you have k complex numbers, and you assume that you raise these numbers to the nth power, you take the sum. This is always bounded by some constant c for all integer n. So for each n, you raise them to the nth power, you take the sum, and the absolute value is always bounded by a constant number c. Then you can show that actually each of these complex number has absolute value smaller or equal to 1. So this is a not very easy lemma, but if you know what a complex number is, you should be able to prove this lemma. And then you just apply this lemma to alpha 1 divided by square root q, alpha 2 divided by square root q, to alpha n divided by square root q, alpha 2g divided by square root q. Then you get the proof of the Riemann hypothesis. I just stop here.